Following up our last video when we introduced the topic of limits of functions, now we're going to look at a couple of examples of limits of functions. So let's take a look at a couple of examples here, some introductory examples before we get deeper into the subject. All right, here's our first example. We're given a graph. This graph is the graph of a function y is equal to g of x. So the graph is shown right here on the screen. We're going to use the graph of this function g of x to find each of the indicated values and limits. So in part A over here, right there, we're going to find the value of g of 3. So what is the value of the function g when x is 3? This is just to get us up to speed here. Well, we see right there, there's where the function is defined. That output is 1. So we are defined at 3. The value of g of 3 is equal to 1. Now, remember, our conversation from the last video about limits was that the function need not be defined at a location for the limit exists as long as the function approaches the same value on both sides of the value of x as an output. Now in this case, in part B, when we're asked to find the limit of this function g of x as x approaches 3, well, we got to look at what this function is approaching as the value of x approaches 3 from both the left and right hand sides. So as we can see, let's start on the right. Here's 3. As I'm approaching x is equal to 3 from the right to the left. Well, what's going on? Well, that function is approaching the output of 1. However, as I go to x is 3 from the left to the right, we're up here now on the top part of the graph. This function is getting really close to the output of 2. So this is an example here where the limit is not going to exist because the function does not approach a unique output value as we get close to the location of x is equal to 3. Right? We got to have the same location being approached as we approach the input value x from both sides of 3. So in this case, this limit does not exist. D and E, as you recall. Erase some of these things right here. Okay, how about let's go find the value of g of 5. Well, here's 5. The output right there, guess what? There is no output, right? That's what that little circle means, that hole looking thing, is there's no numerical value at that location. Hence, g of 5, there's nothing there. It's undefined. Now, we're then asked in part D to find the limit of this function g of x as x approaches 5 and relate that really to the value of the function g at 5 where it's not defined. So again, as I get close to 5 from both sides of this value of x is 5, what's my function doing? It's getting really close to the output of 1 on both sides of 5. And, you know, again, even though the function is not defined at x is 5, that does not define the limit. All we care about is as x, or the input value, gets arbitrarily close to the value of 5, the function is getting really close to a unique output value, but not necessarily equal to. And in this case, it happens to be 1. So in that case, limit as x goes to 5 of g of x is equal to 1. And the limit exists. So right here, this example is supposed to give you an idea that if I'm given a graph of a function, should be able to find the limits of this function graphically by playing the same game that we just did. So there's your first example. So just real quick, one way to find limits is graphically, if we have a nice graph that's very accurate. Another way to find limits is numerically. And this is the example of a numerical example. As you can see, we have a table. what we have given to us is a function k of t here, which is defined to be t cubed minus 1 in the numerator divided by t minus 1. We're going to construct this table of values to find what the limit as t approaches 1 is of this function k of t. Now note, if I plug in t is 1 here, right? If t is equal to 1, then notice when I plug that in, k of 1 is going to equal to 1 cubed minus 1 over 1 minus 1, which is 0 over 0. That's not defined. It's undefined. So this function is not defined at 1. However, could it be that the limit exists? Well, that's what we're going to have to see. So eventually we're going to develop algebraic techniques to come up with some of these limits, but we're not quite there yet. And here is an opportunity to we're going to plug in values really, really close to 1 on both the left side of 1 and the right side of 1 to see if the outputs of this function k here approach the same thing or not. So it's a matter of plugging in all these different t values that I've constructed in the table into the function and noticing a pattern. Now, if no one gives you such a table, then you can always construct a table for yourself. And that is, notice we're trying to approach 1 here in the t direction. So if we want to approach 1 in the t direction on both the left and right hand sides of 1, then what we want to do is get really, really close to this location of 1 from both sides. So let's pick numbers really, really close, right? How about on the left side of 1, t is 0.9, or t is 0.99, or t is 0.999, and you get closer and closer to 1 until you feel confident that you're reaching a certain output limiting value if it exists. Same thing goes on the right side. So right here, here's of course left side of 1. And then these next 3 entries, the values of t to the right side of 1. Right side of 1. So you just pick values, get them closer and closer to 1, like 1.1, 1.01, 1.001. Get as close as you can until you start noticing some distinct pattern. So to spare all the computations, I've went ahead and already computed what the output values of this function k is at these various values of t. T is 0.9, ends up that the output value is 2.71, and you can verify this. If t is 0.99, the output is 2.9701. If t is 0.999, the output is 2.997001. So it sure seems like this function is getting really, really close to, say, 3 as we get close to 1 from the left-hand side of 1. What about these other values? Again, I've gone ahead and already predetermined them by computing them, but you can verify it if you need to be. At 1.1, the output of k is 3.31. At 1.01, the output is 3.0301. And at 1.001, the output is 3.003001. So as we can see in this table, as t is getting really, really close to 1 on both the left-hand side and the right-hand side of 1, it sure does seem like that this function is approaching the output of 3. So all this seems to show, right, now we're not 100% confident, but this helps us have some confidence, seems to show that the limit as t goes to 1 of k of t is equal to 3. So we should feel pretty good that that's true, unless there's some crazy thing happening closer and closer to t is equal to 1 that we have yet to determine. But this table is supposed to help us establish those patterns. And in my opinion, it's enough to establish that fact that seems pretty true that as t approaches 1, the function approaches 3 on both sides of t is equal to 1. We can show this to be algebraically true, but we first have to establish some things that are called limit laws in order to do that. So in this case, we're going to say, you know what, feeling pretty good that this is true. Now, if you graph this using some software or even by hand, your function is going to look like this. Happens to be that when t is 1, say it's t down here, my bad, that there's a little hole in the graph. That hole, or otherwise known as a removable discontinuity, shows that as we are approaching t is 1 on both sides of 1, this function is indeed getting closer and closer to the output value of 3. And so it's nice to see that graphically as well, because it verifies what we constructed in our table to be true. Now, if you ever construct a table like so to try to figure out what a limit is, and it's not consistent with the graph, then you know something's going wrong somewhere. But in this case, everything is consistent. We're feeling pretty good. And like I said, eventually we will be able to algebraically manipulate this function as so, and actually have a more conclusive statement that the limit is indeed 3 here as t approaches to 1. So it's just a couple of examples to get you going, in the sense that before we develop our algebraic methods, we could always get the graph of function, look what's going on there. We could also create tables of values, get closer and closer to the input value of concern and see what's going on there. Graphical methods, tabular or numerical methods, and then eventually we'll develop algebraic methods. So that's just a couple of initial examples to get us going. So hopefully you'll be able to go do a few of these on your own before we develop further methods. All right, that's it for the video. Math and beats. Later now.